Greetings and welcome to Distilled. In the previous lecture, we talked about list comprehensions and we solved a very simple example on linear regression. So today we'll be talking about linear regression in chemical engineering. So I have tried to get examples from a few core areas of chemical engineering, but this can be applied to other areas, other interdisciplinary fields as well. So I would be so apart from the examples that we covered today, I would love for you all to explore more options wherein you can apply the concepts of linear regression that you've just learned. And I would be very happy to learn more about them. So please make sure that you mention all of that in the comments section. And yeah, so let's begin with today's lecture. So when we talk about linear regression, we see that this linear regression is a model that establishes linear relationships between two variables, x and y. Or if we are dealing with multiple variables, then all of the variables should be linearly related to each other, right? So if you come across any equation that can be written in this form, is where you can apply linear regression. It is not necessary that the equation have should be linear in principle. So, for example, if you have an equation which relates pressure and temperature as pressure equals to E to the power AT, right? So, in that case, in principle, this is not a linear equation, but this can be linearized by taking a natural logarithm of pressure. So you'll get ln P is equal to AT, right? So in that case, you can consider Y as ln P and T as X, right? So you can linearize equations or you have linear equations simply. All of them, for all of those cases, you can use linear regression. So we'll start with kinetics. A very interesting example comes up here. So any reaction A to B with an order n can be written in this way. This is the rate law, where rate of disappearance of the reactant A is given as kCa to the power n, where k is the rate constant and n is the order of the reaction, right? So if I consider a constant volume reaction, then this volume term goes inside the derivative and you get number of moles by volume, which is the concentration, right? And then if we integrate this, we'll get this. And naturally, at time t equals to 0, the concentration of A is the initial concentration of A. And at time t equals t, the concentration of A is C, right? So if n is not equal to 1, you get this equation. And if n is equal to 1, you get this equation. Now, in principle, these equations are not linear. But if you consider this term, 1 upon Ca to the power n minus 1 as y and t as x, or similarly, if you consider ln Ca as y and t as x, so in that case, you can apply linear regression to this, right? But this is a little more challenging, especially if the order is not known. Because if you see the y variable itself, it depends on the order, right? So from the laboratory, you will be able to get a concentration versus time data, but you would have to estimate the order. So one way that I uh, prefer doing in if I have to follow this method would be that I would guess some value of n and generate an x and y data. And I'll keep on generating multiple x and y data for different values of n, right? And now I have Ca. So for a given value of n, I'll be having the values of y. And then for those x and y data, I would calculate the coefficients, which is beta naught and beta 1, and I'll see if which of them fits the equation best, right? So in order to calculate that, I would use R square value. So whichever value of n gives me the best R square value, I would say that this is the order, this is the approximate order of the reaction, right? But that is still a little more challenging. So another way you could do is by directly using the rate data, because this is the rate law minus Ra equals to Kca to the power n. So you could directly linearize this by taking a natural logarithm of the rate minus Ra. So in that case, you get ln minus Ra equals to ln k plus n ln ca. So here, even if the order is not known, you would be able to get the order from the slope and the rate constant from the intercept. That is, beta naught will give you ln k and beta 1 will give you n, right? So you can consider ln minus Ra and ln ca as y and x respectively, right? But then again, from the laboratory, you will get concentration versus time data. So how do you obtain rates? So it's actually not as challenging. To get rates, you can use numerical differentiation. So as long as your time difference is not very large. So considering that, let's say, a reaction goes on for 10 minutes and you've taken a concentration measurement at every, say, 10 seconds or 30 seconds, then in that case, it is safe enough to use numerical differentiation. This over here is a forward difference formula that I have written. You could use multiple variations, a backward difference or a central difference formula to enhance your accuracy. But yeah, you can numerically calculate the rate values and then use it to estimate the order and the rate constant. The only thing in that case would be that you'll need a lot of data of concentration versus time. Okay, you cannot expect that if it's a 10-minute reaction and you have uh, a reading of concentration at, let's say, 3 minutes, another at 6 minutes, another at 9 minutes. So in that case, these are very few data points, and the rate values that you'll get from here would not be very accurate. So that is not something that I would suggest. But I would definitely say if you have a lot of data points, let's say a reaction goes on for 10 hours and you have taken a reading every 10 minutes or every 30 minutes, in that case, rate would not change significantly. Uh, and you significantly as you go from one reading to another. And therefore, you would be able to get more accurate instantaneous rates. So that would be a good way to go about it. Okay. So this is an application of linear regression because you can linearize this equation. Similarly, for the previous thing, you could again linearize these equations. So you will be able to get the rate constants out of this, right? Another very interesting application comes in enzyme kinetics. So enzymes generally follow what is known as a Michaelis-Menten kinetics. So this equation was derived. It is it is actually derived in a lot of classes where kinetics is taught by using the mechanism that was suggested by Michaelis-Menten to derive the enzyme kinetics equation. So we use a few assumptions and a few approximations to come to arrive at this equation, right? So if you see this in principle is not at all a linear equation. You see this kind of a plot where Rm and Km are Michaelis-Menten constants. Rm is the maximum rate of the reaction. So for a very high concentration of the substrate, uh, the rate approximately asymptotically reaches Rm, right? So for a very high concentration of CS, that would be a very high rate of the reaction, right? So this is in principle not at all uh, linear, right? But what you can do is you can linearize this by taking a reciprocal of R. So when you write it as 1 by R equals to 1 by Rm plus Km by Rm into 1 by Cs. So you see 1 by Cs and 1 by R. It is linear in 1 by R and 1 by Cs. And 1 by Rm and Km by Rm are the parameters. So you can consider 1 by R as Y and 1 by Cs as X. And you would get the constants 1 by Rm, which is beta naught, and Km by Rm, which is beta 1. So this can be used to estimate the values of Km and Rm. And this kind of a plot, the linear plot between 1 by R and 1 by Cs, is known as a Line-Weaver-Burk plot. And this plot is used to estimate the Michaelis-Menten constants. In few books or in few lectures, you'll see people often use the term V rate, instead of R for rate. So they consider this to be reaction velocity. So it has the same meaning as long as the units of V and V max, they have to be the same, right? So it could be either R and RM, or it could be V and VM or V max, right? So this is another application where you could use linear regression. We could also study temperature dependence of reactions, and that again is a good application of linear regression. So Arrhenius equation gives you the temperature dependence of rate constants. So K is equal to A e to the power minus EA by RT, where A can be considered as an Arrhenius constant, and EA is the activation energy of the reaction, right? Which is an activation barrier that the reaction must be able to cross this activation energy in order to form product, right? So this again principle, it is not a linear equation. But if we take a natural logarithm of k, so you will get ln k is equal to ln a minus ea by r into 1 by t. So you see ln k can be considered as y and 1 by t can be considered as x. So now it is again y equals to beta naught, which is ln a, plus beta 1 x. So beta 1 is minus ea by r. And you can definitely get the values of these constants from your model. So once again, you just need a rate constant versus temperature data, and you will be able to calculate these constants using linear regression. And from the previous slides, you already know that rate is equal to k Ca to the power some n. So since rate is proportional to k, this equation can very nicely be extended to rate as well. You can say ln r is also equal to ln some constant minus ea by r into 1 by t. So that some constant would be a function of the concentration, but as long as you maintain the concentration at a fixed value and you just change temperature. So for example, if you carry out a reaction at 300 Kelvin with zero point 0.1 molar of some reactant, and then you carry out the same reaction with zero point 0.1 molar of the reactant but at 500 Kelvin, and you take the rate measurements. So again, you can use those data points to evaluate uh, to evaluate the activation energy. Other thing that you could possibly do is you could calculate rate constants for uh, the rate. You could calculate rate constants and the orders of the reactions for different for the concentration versus time data at different temperatures. So you'll get rate constants at different temperatures, and then you could use this equation to get y versus x. So you could go ahead and do some uh, logical application of this, but you can get all of these constants using linear regression. So it's a very interesting application of this. Then we also find these applications in thermodynamics. So for example, there are Henry's laws. So Henry's law is something uh, that relates the partial pressure of a gas to its solubility in the liquid phase. So if a liquid and a gas, they are in equilibrium with each other, so its solubility is linearly or basically it's proportional to the partial pressure of the gas in the liquid phase. In the vapor phase. All right. So this is sorry. The partial pressure of the gas in the liquid phase. Yeah. So concentration or the solubility of the gas is proportional to the partial pressure of the gas in the liquid phase. Right. So uh, this can be written as xi equals to kh into pi. So kh is the Henry's constant, and this law is very very valid for dilute solutions where Xi is very small. So you could use a data for partial pressure versus concentration or versus the mole fraction to get this Henry's law constant. And this again can be formulated as a linear regression problem. Another thing that you often see in thermodynamics is equation of state. So equation of state is something that relates pressure, volume, and temperature. And these equations of state help you to predict um, the volume occupied by the gas, let's say, at a given pressure or temperature. Or similarly, it helps you predict the temperature of the gas at a given pressure and volume, and so on. You could go ahead and use this equation of state. And it is very widely used in thermodynamics to calculate thermodynamic properties of specific substances and all of that. So um, when we are talking about low pressures, then most of the gases behave like ideal gases, which means they follow the ideal gas equation of state, PV equals to nRT. But at higher pressures, these gases start to deviate from ideality. And that is because they start interacting with each other. And when we talk about ideal gases, they do not interact with each other. So different molecules of ideal gases do not interact with each other. And because of that, it behaves in an ideal form. But when you increase the pressure, that interaction comes into the picture. And that interaction can be modeled by different methods, which help us get different equations of state. So we heard we have one simple equation of state, which is the van der Waals equation of state. So van der Waals equation of state uh, brings a pressure correction and a volume correction into picture. So the pressure correction is this, sorry, the pressure correction is this term, A by V square, and the volume correction is this term minus B, right? So these terms are responsible for the non-ideal behavior in at a moderate pressure, right, or a higher pressure. So any gas, let's say, if it follows or it is known to follow a van der Waals equation of state, and let's say you want to estimate these parameters A and B. How would you do that? So we could design an experiment in a way such that we keep, let's say, the volume constant. And how would we do that? We would take a rigid container and we would make sure that no gas escapes out of that container. And we keep on pressurizing it, keeping the volume constant. And once we pressurize it, we note its temperature. So now what happens? Volume is constant, pressure is varying, temperature is varying. So you see, this can be written as P equals to R upon V minus B times T plus A by V square. So this equation is a linear equation in temperature. So from there, you can get beta naught, which is A by V square. V is constant. So you'll be able to get A, right? And similarly, you get beta 1 as R upon V minus B. Once again, R is the gas constant and V is also maintained constant. So you'll be able to get B. So by observing a pressure versus temperature relationship, you will be able to get A and B values, right? So therefore, by cleverly designing your experiments, you can make the equation act like a linear equation and then use linear regression there. Another thing that is another equation that is very widely used in thermodynamics is the Clausius-Clapeyron equation. Clausius-Clapeyron equation relates the vapor pressure to the temperature at, or basically the saturation temperature and the saturation pressure in a vapor liquid equilibrium. All right. And this is derived from the Clapeyron equation by making a few approximations. And we arrive at this particular equation. All right. So now once again, let's say we want to calculate the heat of vaporization uh, for this particular gas. And let's say heat of vaporization is constant, or if we are doing it over a temperature range, we could say that the heat of vaporization that we get from here is an is an average heat of vaporization. Then how would you get this heat of vaporization? So if you see in principle, this equation is not linear. But if we consider this term as y, ln p vape by p vape naught as y, and 1 upon t naught minus 1 upon t as x. So then this becomes a linear equation, right? This becomes a linear equation, and you can get delta H vaporization by R. One thing to note here is that based on what x and y values we had taken, the two equations here, Henry's law as well as the Clausius-Clapeyron equation, do not have uh, uh, an intercept. So beta naught is not there. But still you can use linear regression here, and the value of beta naught that you will get, it has to be very, very small. It would not be exactly equal to zero, because if you put that exactly equal to zero, you are forcing um, your you're forcing one data point, which is not right. So beta naught would not be exactly equal to zero. There would be some small value, but it has to be very, very small value. If it turns out to be a very large value, then there is something wrong with your linear regression model, or it's not something that can be possible for this particular. So beta naught must be as low as in such equations, right? We can also apply this to fluid mechanics. So, for example, often in complex flows, you see that flow rate can be modeled by saying that it is dependent on different properties, let's say velocity or diameter of the pipe or viscosity. And it is not exactly linearly dependent, it is dependent on some power of these quantities. So again, if we take a natural logarithm of the flow rate, and we get this sort of a linear equation. Now, this is an example of a multiple linear regression, but over here again, you can fix some of these quantities. For example, you can fix D and you can fix mu, right? And you can obtain uh, lnv, right? So in that case, you'll get an equation between, so in that case, beta naught becomes ln k plus blnd plus cln mu, and beta 1 becomes a. So that way you're able to obtain the value of a. Similarly, now you can fix the velocity and change diameter, right? So in that case, you get ln k plus alnv plus cln mu as beta naught, and beta 1 would be b in this experiment. So you will get the value of b. Similarly, you can fix um, velocity and diameter and vary viscosity by taking different fluids, right? And you can again plot ln q versus ln mu, and c would give you the beta 1 value. Beta 1 value in this case would give you c. And then based on one of the experiments, um, you can get lnk as well, right? So that makes it very simple. But again, this can be solved using multiple linear regression as well, where you can simultaneously uh, simultaneously vary velocity, diameter, mu, and you can perform some matrix operations to get all of these constants, uh, and you can evaluate them. But we have not moved on to more complex operations because we are still just getting familiar and getting comfortable with lists. So I don't want to push you over there. But this can be a good application of multiple linear regression as well. Okay. Another example is in flow in a capillary. So flow in a capillary is driven by surface tension. Surface tension pulls fluid and it allows it to flow ahead in the capillary. And this surface tension force is balanced by the viscous force. And if we have a vertical capillary, it would be balanced by viscous as well as the gravitational force, right? So by a so this equation over here is uh, obtained by doing a force balance in a horizontal capillary. So in a horizontal capillary, it's just a viscous force against the surface tension force that is pulling it. So in that case, you get this dependence of length traveled by the fluid in this capillary versus time. Okay. So once again, this is not linear, but you can consider root t as x and L as y, right? So this becomes linear, and you'll be able to evaluate this coefficient, which is the Washburn coefficient. Washburn coefficient can be analytically obtained using force balance. So based on the surface tension values and everything, you can get these the Washburn coefficients. But for more complex scenarios where you cannot blindly say that, okay, there could be some sort of losses here and there, or there could be some issues with um, the way I've carried this force balance, and this just becomes a model in that case, not exact. Uh, this doesn't exactly capture the physics, let's say. But still, if this is a model, so you can calculate this Washburn coefficient using uh, linear regression. And once again, this does not have an intercept, but you are not supposed to force a beta naught equals to 0. So you're supposed to calculate beta naught, but that beta naught has to be a very small value, right? Similarly, you can apply this to transport phenomena while you are trying to figure out a dependence of these uh, terms such as viscosity, thermal conductivity, diffusion coefficient. If you see, these all are functions of temperatures, right? So you can get a mu versus temperature data, K versus temperature data, D versus temperature data, and you can try to fit it to a non-linear equation. And again, you can linearize that, and you would be able to get some sort of a dependence, the dependence on that. So you, and a lot of equations are available, empirical equations are available. Uh, but yeah, all of those parameters can be very easily obtained by fitting experimental data to uh, those models and evaluating the uh, parameters. And linear regression is used for that. So you can evaluate the parameters beta 1 and beta 2, beta naught. Yeah. So these are a few applications. You could tell me a lot more about the applications that you come across in your field of research or anything that you are up to. So definitely, if there is something new that you've learned and you feel that linear regression could be applied to that, please do tell me. Please do mention that in the comments over here. Okay, now we move on to doing a few examples of whatever we have studied so far. So I have two example problems for you. One is from kinetics and one is from thermodynamics. Okay, so I have enzyme kinetics given over here. So as I told you, I'll have data for rate versus substrate concentration. So this rate has, let's say, been measured somehow, and I have the substrate concentration over here corresponding to this rate, right? And now I want to calculate the um, Michaelis-Menten parameters, Km and Vmax, right? So how would I do that? I have this as the Michaelis-Menten equation. So I linearize that to get 1 by V naught equals to 1 by Vmax plus Km by Vmax times 1 by S, right? And now this is a linear equation in 1 by V versus 1 by S. So beta naught is 1 by Vmax and beta 1 is Km by Vmax. So let's try to uh, code this thing based on whatever linear regression we had studied in the previous lecture. So I have written these values for both the examples. So substrate concentrations are in this list S, and the velocity or the rate values are in this list. Okay. So now, as we said that we'll be using list comprehensions quite extensively now. So let's start with that. So in my problem, X is 1 by S. So let's make up an X array. So X array is 1 by S. So I would write it as 1 by I for I in S, right? So this is what we want to append And this is what we'll write as the for statement. This is what we'll write in the for loop, uh, for starting a for loop, right? So this is X. And Y, we had said it is 1 by V. So similarly, this is what we'll be appending, and this would be the for loop, right? So I have X and Y data ready. Now, N is equal to the length of X, right? We need X bar mean. So that is sum X upon N, right? We need Y bar, which is mean of Y. So that is sum Y by N, right? Then we also need summation of xy and summation of x square. We don't need these specific values. So let's just say summation of xy is sum, and within the brackets, we'll make up the list. So let's make up the list. So that is xi times yi. So since we are taking elements from two lists, we are not going to use I in S or I in V. Rather, we are going to say I in range N. N is the length of the list. So this accesses the X, um, the value from the list X with index I, and this accesses the value from list Y with the index I, right? And this thing creates the list while this command takes the sum of that list, right? So we've got that. Similarly, X square is simply I square for I in X. So this has created the list, but we don't want to store it. So we'll just put the entire list directly in the sum function, right? So that is done. Now we just need to evaluate beta 1. So based on the formulas, beta 1 is x bar y bar minus summation of xy, which is xy here, upon n, whole by x bar square minus summation of x square, which is x2 here, by n. That gives us beta 1. Beta naught is y bar minus beta 1 times x bar, right? What would be the y predicted? Y predicted would be beta naught plus beta 1 times the values of x. So I for I in x, right? That is y predicted. So let's plot this. So import matplotlib dot pyplot as plt. Although I always prefer importing all the libraries in the first line itself, but it's okay. Let's go ahead. So import matplotlib.pyplot as plt, and now we can just plt.plot x comma yp, because this is going to be a straight line which follows the equation beta naught plus beta 1x, right? But the data points that we have, that would be a scatter plot. So scatter x comma y, and if we run this, we'll get the plot here. So if you see over here, the data points that we have, they are very, very nicely fitting this line, right? So it's a good fit over here. And how to measure whether the fit is good enough or not? We'll calculate the R square value. So what is R square? R square is 1 minus sum of squares of residues. So once again, we don't want to store the squares of residues, but we need to calculate its sum. So let's make up a list that calculates the residues. That is I, sorry, yi minus y predicted I whole squared, right? That is the squares of residues for I in range n, right? So that becomes the list of all the squares of residues. And then we'll just calculate the sum of these because we do not want to store this, right? So we've got this. And then we also need the total sum of squares. So once again, let's create the list of total sum of squares. Total sum of squares is just I minus y bar whole square for I in y, right? So yi minus y bar, which is I minus y bar here, because we've taken all the values in y, right? And again, we don't need to store this list. So this becomes sum, right? And now we have the R square formula. Let's just print R square for this. And if you see, the R square is actually very, very nice. Very, very nice. So we have a very good value of R square over here, right? It's very, very, it's approximately 1 if you see. That is because it is fitting very well, right? So this gives us the coefficients beta naught and beta 1, but the objective of the problem was to calculate Km and Vmax. So if we go back to our equation, we see 1 by Vmax is beta naught. So from here, we get Vmax is equal to 1 by beta naught, right? And Km by Vmax is beta 1. So Km is equal to beta 1 times Vmax, right? So we'll get the uh, parameters here. And let's just, for the fun of it, let's just make up another figure. So over here, I'll just put plt.show, and let's just plot the data of S versus V and the S versus V that we predict from the Michaelis-Menten equation, right? So let's say we predicted from the Michaelis-Menten equation would be Vmax times substrate concentration upon Km plus the substrate concentration for I in S, right? And let's just plot the substrate concentration, that is um, S versus V predicted. And let's just do a scatter plot of the substrate concentration versus the V data that we had. And if we do this, you see the curve looks something as I showed you in the slides. So it's something like this. The curve is something like this. And this asymptotically reaches Vmax. So let's just see what is the value of Vmax. So Vmax is 1.2. So you see over here, it's going slightly above 1. So it's approximately reaching 1.2. And if you see Km is 0.25, which is somewhere here. And if I see Vmax by 2, that is 0.6. So you see from this equation, 0.25 is somewhere here itself. Yeah. So that is what we had seen in our slides as well, that um, corresponding to rate equals to Vm by 2, the substrate concentration becomes equal to Km. And that is what we see over here, approximately equal to 0.25 something when we have the substrate concentration approximately equal to 0.25 something. The rate becomes approximately equal to Vmax by 2, which is 0.6 something, right? So this equation follows Michaelis-Menten kinetics very nicely. This enzyme basically follows Michaelis-Menten kinetics very nicely. That is our conclusion from this example. And you can use the same format for calculating Km and Vmax for any other data set that you have. And in fact, you would often see that uh, when you talk about enzyme inhibitors, so this is again taught in kinetics courses, when we talk about enzyme inhibitors, based on the kind of inhibition that uh, the enzyme, uh, based on the type of inhibitor that you are introducing in your enzyme, the values of Km and Vmax change accordingly, right? So you have so once again you take rate versus substrate concentration data, and you observe which kind of inhibition it is by comparing values of Km and Vmax. So you'll have to do this exercise for different data sets, which again gives you the values of Km and Vmax. And then by comparing the values of Km by Vmax in presence of the inhibitor and in absence of the inhibitor, you will be able to figure out which kind of inhibition is seen in this problem, right? So that is the first problem that we have solved. Okay, so hopefully that is good to go. Now we move to the next example, which is on Clausius-Clapeyron equation. So whenever we try to predict vapor pressure is a function of the temperature, the transition temperature, right? So an equation known as Antoine equation is used to predict vapor pressure as a function of temperature. All right. So over here we have this Antoine equation with A, B, and C as Antoine coefficients, right? So for water, these coefficients are given to be 8.071 and so on, right? And temperature over here, this is very important. You must know what units uh, these vapor pressure and temperature are in, because based on these units itself, the values of A, B, and C are calculated. If I change these units, let's say if I make the vapor pressure in ATM or if I make the temperature in Kelvin, the values of these constants will be different, right? So this is very important. Not just here, in any empirical equation, if there are certain constants, it is very important to know that what are the units of the physical properties that are evaluated using that empirical equation. Okay, so now we have the Antoine coefficients. So the first part of the problem is to generate a data for vapor pressure as a function of temperature for temperatures between 25 and 35 degrees Celsius. So let's do that. So over here, I just comment out the first part of this thing. I'll comment out the first example here. And then let's make a list of all the temperatures that we have, right? So we'll use list comprehensions here. So we'll start with T equals to I for I in range, starting from 25 and it should stop at 35. So the last value is 36, right? So this gives me a temperature array, right? Let's now calculate ln P vapor. So that is A minus B upon C plus T. So we have A, we have B, C plus I for I in T. Very simple. If you would have gone with the conventional method of using a for loop, this would have been multiple lines. But now you see just 2 lines of code, right? Okay. So now we have the logarithm of vapor pressure versus temperature. So the first part is over. If you want to get P vapor data, you can just say that is first let's import a math module. So import maths, and we could just say P vapor is equal to um, P vapor is equal to math dot exponential I for I in ln P, right? So this gives you the vapor pressure, but we'll be using ln PV more. So yeah, this is something that you can do, right? Okay, let's move on to the next part of the problem. So the next part of the problem states that assuming that Clausius-Clapeyron equation is applicable. So just assuming that for the given range of temperatures, the heat of vaporization is not a function of temperature, which is one of the major assumptions you take while deriving the Clausius-Clapeyron equation. So let's say heat of vaporization is not a function of temperature. So you'll get the heat of, so from the Clausius-Clapeyron equation, you'll be able to estimate this delta H wave. So let's do that. So you see Y is ln P vaporization by ln P vapor naught. So I'll just take P vapor naught as the first value, right? The first value in my list over here. So ln P vapor by P vapor naught can be written as ln P vapor minus ln P vapor naught. So that is my Y. So let's form my Y array. So Y is ln P vapor, let's just call it I, minus ln P vapor naught, which is the 0th value of uh, this array for I in ln P vapor, right? So from here you see that for the first value, this would be 0 and then it would increase, right? Fine. Then from here we see x is 1 by T naught minus 1 by T. And one thing that you have to keep in mind is that this temperature is not in Celsius, it's in Kelvin. So we'll have to add 273 when we are doing this calculation. So when we do the x calculation, that is 1 by T naught, which is the first value of T, and we add 273 to convert it into Kelvin, right? Minus 1 by I, and once again we'll add 273 to convert it into Kelvin for I in T, right? So we have x and y data, okay? And then once again we'll follow the same method that we did here. So I'll just copy and paste the entire code over here. So from here, let's just copy and paste the entire thing. So I've already defined x and y. That is not needed. We've got the length, which is the number of data points here. I'll just comment it out. So yeah, we've got the length, we have got the mean of both, we've got some xy, we've got some x square, we've got beta 1, beta naught, and we got predicted values of y for a given x, right? Now let's just see what these values are. And you see the plots are the plot is very, very nice. So naturally our equation has been fit very well. Now, if you remember, I mentioned that in this kind of an equation where it is y equals to mx form, you do not have a beta naught here. So you cannot ignore beta naught in your model. You'll have to consider that, but that beta naught would be a very small value. So let's see what is the value of beta naught here. So as you see, beta naught is very, very small. It is very, very, very small. And if you see beta 1, it's a big enough value, 2289.84, right? So this is very useful for us. And now let's just calculate delta H vaporization. So dH vaporization is beta 1 times, so delta H by R was beta 1. So dH vaporization would be beta 1 times R, which is 8.314. And the unit of dH vaporization, because if you see, uh, this is dimensionless, right? And this is in the dimensions of 1 by Kelvin. This, so the dimensions of delta H vaporization would be the dimensions of R multiplied by Kelvin, right? So R over here is 8.314 joules per mole Kelvin. So therefore, the dimensions of delta H vaporization would be joules per mole. But generally, heat of vaporization is calculated in kilojoules per mole. So we'll just multiply 10 to the power minus 3 to this thing, right? So this becomes a delta H vaporization in kilojoules per mole. So if we see, the heat of vaporization is approximately 19 joules per mole, right? Uh, that is the value that we have got. So you can compare this value with the values you get in steam tables. So I've also taught you about steam thermodynamics. So over there, I have taught, I showed you how to read steam tables. So you could go there and have a look. But this is the way to calculate the heat of vaporization. And you could use similar methods here we used in the previous example to calculate R square. So let's just do that. Um, so I can calculate R squared value, and my R square value is again 0.999 something, approximately equal to 1. So this is a very, very good fit. And you can see that from the plot itself that almost all data points are lying exactly on the line. So the fit is very nice. So these are a few examples of linear regression. You could have multiple such examples in the chemical engineering courses that you're taking, or in your research if you're doing that. You could come across multiple such examples, and you could apply these concepts there. So this could be very, very helpful. And yeah, I have uploaded the self-assessment test for this one as well. You'll find the link for the same in the description. Please make sure that you attempt self-assessment tests because they are very useful and they would really help you get comfortable with concepts of, let's say, complex concepts like list comprehension, because people find this to be challenging when they are just introduced to it. And I highly recommend you therefore to attempt self-assessment tests to be more comfortable with these concepts. Thank you.